Thank you. So this talk is about crafting your query DSL with NimbleParsec and Ecto. So a little bit about myself. I'm Riccardo Binetti. You can find me online as Urbino. I'm a senior software developer at SecoMind, and fortunately, I'm using Elixir as my main language since 2017. So first of all, what we mean as query DSL. So our goal is to perform complex filtering on a list of resourcing using a user-defined selector. So in this case, we're going to use shapes as our test subjects. Nice. And basically, they're going to be represented as a struct and as an SVG visually. So basically, shape can have dimensions. So they can be either small or big. They can have a different number of sides, between 3 and 9, and they can have different colors. So our goal is, given a list of shapes, we want to be able to write something like this, so small or sides greater than 6 and not blue, and we want to select just the shapes that match that selector. The feature of our DSL are going to be equality filter for color and dimensions, comparison filter for side count, and arbitrarily nested and/or expressions. So we have operator precedence, parentheses, and negation, all the goodies you'd expect. We're going to do that in 2 different steps. First, we're going to parse the DSL in a struct-based AST, and then we're going to compile the AST into an Ecto dynamic query. So let's first look at the first phase of our parser. And to do that, we're going to use NimbleParsec. NimbleParsec is a simple and fast library for text-based parser combinators. And basically, with NimbleParsec, you build a parser by composing combinators. And each combinator can consume some input, produce some output, combine or modify the effects of other combinators, and combine or modify the produced output. And it can also do a combination of those things. It can also do other things like manipulating the context, which is an internal state of the parser, but we're not going to use that for our example today. So in NimbleParsec, combinators are functions. So it's easy to compose them, either piping them one through the other, or you can use other combinators to combine them. When you're done with your combinator, you usually pass it to the devparsec macro, and the devparsec macro outputs an highly optimized parser. And there are no runtime dependencies for that. So I'm going to show a subset of all the combinators available in NimbleParsec, and we're going to try to do that one combinator at a time. So let's start by parsing a dimension filter, but actually we're just going to start by parsing the string small. So as you can see, we are defining a module, importing NimbleParsec, and calling the devparsec macro with an atom as first argument, which is going to be the name of the function, the parser function that gets generated. And then we're going to pass our first combinator, the string combinator. The string combinator accepts a string as parameter and outputs and accepts and outputs that string in the parser output. So after we compile that, we can call parser.dimensionFilter with the string small, and we can have a look at what NimbleParsec outputs by default. So it's an OK parsing, so it's the atom OK. Then the second return value is the list of all the outputs of all the combinators. In this case, we just have a single one. Then the third return value is the rest of the input, and we're going to see a little bit more about that in a little bit. And this is the context. So as I was saying, we're not using the context, so it's just going to be an empty map for us. And then this is some line information telling you that you're at the first line, the next new line was at the 0 offset, and then you parsed 5 bytes, basically. So all is well, but our dimensions are small and big. And right now, we're not able to parse big. So what we're going to do is introducing a new combinator, which is called choice. The choice combinator accepts a list, and basically a list of combinators, and it tries them in order and returns the output for the first succeeding combinator. In this case, we are passing the two small and big string combinators. And just doing that, we are able to parse the big string and output the big string. Now, the next problem is that if we pass smallville, we actually return OK with small, and the parser said, now this vil stuff is left. So we don't want to do that. We just want to parse the exact strings we expect. To do that, we introduce another combinator, the EOS, or end of string combinator. And here you can see that we are combining the combinators by just piping the output of one to the input of the other one. And the EOS combinator basically ensures that at the end of parsing, we consumed all the input. And you can see that from here, because now if we pass smallville, we are just going to get expected end of string, et cetera, et cetera. So almost there for our dimension filter. We also want to actually output an AST, a struct-based AST, as I was saying. So instead of outputting the string, we are going to use the replace combinator. And the replace combinator replaces the output of the combinator that is passed as input with a fixed value. In this case, we extracted the small and big combinator to separate variables. And as you can see, we are able to just pass them inside choice. So this is how you can split big combinators into smaller one. And we are replacing the small string with a dimension filter with dimension small, and the same for big. And you can see in the output that we are actually outputting a struct. So basically, our dimension filter is done. Let's pass to the color filter. And actually, the color filter is very similar. We are still matching for equality on atoms. So we use the dimension filter as a variable instead of using it directly in DevParsec. Then here you can see the powerful nature of NimbleParsec and the fact that everything is just an Elixir function. Here we are able to extract the different color values directly from Ecto enum and map the color atoms by passing them to atom to string. Then we pass it into the string combinator. And then for each of them, we replace them with the color filter struct and the correct color. And then we pipe all of that inside the choice combinator. And after that, we are going to define a new parsec called filter, which is going to be either a dimension filter or a color filter. And as you can see from the output, now we are able to parse both color filters and dimension filters. So now we can switch to the side count, which is a little bit more involved. So we want to pass a string like this, so sides greater than 4. So our filter will be composed of the string sides. Then we have a choice combinator that is going to choose between the different numeric comparison operators. And here you can see an important part. Since they are tried in order, we have to put greater than or equal before greater than. Otherwise, if we switch them, it will always match the first one and never the second one. So this is something you have to consider when using choice. They always go in order. And this is the new combinator we're introducing in this slide. It's the integer combinator. And as you can guess, the integer combinator parses a string that represents an integer. In the argument, you can either pass a fixed value, like 10, that means it should have 10 digits, or you can pass some minimum or maximum amount of digits. If you pass min 1, you are basically saying just parse an integer of any length. And with all that, we're able to parse sides greater than 4 and return. In this case, you can see that the output is not a single value, but it's 3 values. It's size, greater than, and 4 as an integer, because the integer returns already an integer. Now, let's see what concat is for. Basically, concat is useful if you want to isolate some combinator in a separate variable. So if we do that, we are isolating numeric comparison operator. We can't just pipe the previous combinator inside the next one, because now it's a variable. It's not a function anymore. But we can use concat to basically obtain the same behavior as before. So the output is just the same one. Concat is used to split your combinator in smaller parts and concatenate them. Now, next step. We want to emit an atom for the operator instead of a string. And we could do it like before, so just saying string replace, string replace, string replace. But since we know that all comparison operator atoms are already existing in the Erlang VM, then we can just map the output of the whole choice combinator to the map combinator. And as you can imagine, the map combinator maps the input it receives with a function, and it outputs the mapped output. So in this case, we are mapping the result of this combinator with the string.toExisting atom function. And you can see we're actually now emitting the greater than or smiley face atom. So next step, the sides part is actually useless. We want to recognize it, but it doesn't make sense in our output. It doesn't have any semantic meaning. So we just wrapped the string combinator inside an ignore combinator. And what this does is that it still requires you to pass the side string, but it will not output it inside the output of the combinator. And after we have those two values, we want to combine them in a struct. And so we're going to use the post-traverse combinator. And basically, post-traverse is a low-level primitive. All other functions that change the output are basically implemented on top of post-traverse or pre-traverse. And you can pass an atom, and passing an atom basically will call the function with that name, and that function will receive these parameters. It will receive the rest of the input string, the current output of the combinator, the context, the line and offset, and it must return the possibly modified rest of the input, the new output, and in this case we are constructing the struct, our side count filter struct, and the possibly modified context. Now, one thing to notice is that here we have the operator first and the integer second, and here it's reversed. This is because both post-traverse and pre-traverse accept the output in reverse order, and they also must return it in reverse order. So in this case, we are just returning a single value, so it doesn't matter, but you have to keep in mind that too. And with this, basically, we're able to parse the size greater than 4 into an AST node with the operator and the value. Now, we just want to add a little nice touch. So let's have some space around this stuff. To do that, between sides, the operator, and the integer, we are concatenating a blank space combinator. And the blank space combinator is an ignored ASCII string. An ASCII string is the ASCII string combinator accepts a string that is made up of any combination of the characters passed in the first list, and as a or a minimum and maximum length like the integer. But now we introduce a small problem because we're able to parse this, but we're not able to parse the string without the spaces. And what can we do? Well, instead of concat, we're going to use optional. And optional basically means that the stuff that is inside can either be there or not, and it will get accepted anyway. So we have our basic selector now. And basically, the filter now is a choice of dimension filter, color filter, and side count filter. And we're defining a private parsec called selector. And it's private because we're just going to wrap it into some utility function that we're either, since we know that we have a single root for the AST, we're just going to pattern match and assert that we have a single root. And we are going to either return the successful parsing or some kind of error with some line informations. And with that, we can filter green, we can filter small, and we can filter sides equal to 3. And we can error on invalid strings. Now, this is the part where you have to draw the rest of the owl, because I don't have enough time to also go through the binary operation, but they're going to be on GitHub. And so after we do also that, we are able to parse the whole string and put it inside this kind of expression. So if you can see, we have a tree with, for example, a not node with an expression inside, a binary operation with an operator, a left-hand side and right-hand side. So the second step now is to compile that into an Ecto dynamic query. And basically, dynamic queries allows you to build dynamic expressions that are later interpolated into the query. To return to our example, we can build a query that does this one piece at a time. So this is much more powerful than just dynamically passing something to the where operator, because you can have a single piece at a time and then interpolate them inside another dynamic query, and so on and so forth. So it can be very deep as a dynamic part. So we're going to traverse our IST. We're going to use protocols, since we have Elixir structs. So we're defining a filter protocol. And basically, the filter protocol has a function that accepts the AST and outputs a dynamic expression. Then, as the next step, we're going to implement the filter protocol for all our AST structs. So for dimension filter and color filter, we are just basically outputting an equality dynamic query on the dimensions and color inside the struct. For the side count filter, we are doing something similar, but since we have different operators, we are pattern matching on the operator and emitting the correct dynamic query, or you could do it with a macro, but not today. And the nice thing about that is that for binary operator, we are just calling filter.where on the left-hand side and filter.where on the right-hand side, and we can just combine the two and with the correct operator that we have inside our struct. And we do a similar thing for not, so we just get the expression and we negate it. And with that, basically, we have done everything. We have our parse function that is going to call NimbleParsec. And then with our selector in end, we're going to call filter.where on the AST, and we're going to obtain a dynamic expression. And then we can have the where to pass inside our Ecto query and call repo.all. So why don't we just put the dynamic query inside NimbleParsec instead of the AST? This allows you to be much more flexible, so we can extend the filter protocol and add a match function that will perform basically filtering in memory. So we pass the same selector, but instead of outputting a dynamic query, we directly compare it with a shape passed as the second parameter, and we output a Boolean value. And by doing so, using the same selector, we can actually filter stuff in memory instead of using Ecto. So a really quick demo, just to see if it works. How does Mac work? OK. So here I have a live view with a list of stuff, of shapes. And I can just do blue, and it will select the blue ones. And I can do green and small, and it will select the green and small one, and so on and so forth. And I can also do like green and red or small. Green and red or small. Green or red and small. OK. And I think that's it. I don't think we have time for questions. So thank you. You can find the code there.